Okay, so often on the AP exam, a question might come up with you're analyzing end behavior of a function, and the end behavior might be different depending on which side of infinity you are looking at. And so I'm claiming this function right here has two horizontal asymptotes. Find the equation of each. And you know, like having two horizontal asymptotes being bounded above and below is something we're actually going to study in differential equations when we start to look at logistical situations. Like, what if there's a carrying capacity, like at the top, that bounds our upper limit, and then obviously maybe the lower limit would be 0. So we have functions that can model real-world situations that have two horizontal asymptotes. But you know, if you want to look at a graph of what that might look like, here's what that function looks like. I don't know if it, yeah, hopefully it shows up on the video here. This is just through Desmos. My scale right now is from like -80 to +80 in the x's, and my y, here's 2, here's -3. And so it definitely appears that very quickly it's starting to kind of almost be a horizontal line slightly above 2, and a horizontal line that's slightly below -2. So the graph starts to behave like two horizontal asymptotes, and the question is, what are those values? Well, you basically have to interpret horizontal asymptotes. That is our connection with what's happening as x goes to infinity, or in this case plus or minus infinity, to look at both ends. So if you look at the limit as x approaches infinity, positive infinity, I mean, like this denominator, like if you think about this for a second, that's always going to be positive, and if you put positive numbers in here, that still 3x stays positive. This is going to behave a lot like 3x. The bottom's behaving a lot like the square root of 2, and then here, root of x squared, I might want to keep that absolute value, because technically the square root of x squared is the absolute value. And that's going to help remind me that, wait a minute, when I approach positive infinity, absolute value stays positive, this stays positive, so this is like 3 over root 2. So of f of x equals 3 over root 2. And then if I approach negative infinity of my function, now all of a sudden this is a negative x because I'm approaching negative values, but my absolute value is still positive. So I'm going to get a -3 over root 2. And that would be equivalent to those symmetrical asymptotes that we had that were just a little bit more than 2, and a little bit less than -2. Okay? Oh, is that the only one? Excellent. Okay. And then, oh yeah, how fun. So evaluating the defining limits. Okay, so just involving signs, these things sometimes come up. And so if we want to think about, okay, the limit as x approaches infinity of just like the sine x. Well, if you're just basically evaluating the sine function and wanting to know what's the behavior as x goes to infinity, all right, our sine wave as you go to infinity doesn't change. It's continually oscillating between 1 and -1. So remember, limits want to predict the behavior as you approach the end, quote unquote, of your function. Well, yeah, the function's very predictable, but it doesn't get any closer to 1 than it does -1. So this actually limit doesn't exist. If you want to use the terminology from earlier, it's dying by oscillation, but just very slowly and just very consistent pace. Okay? So this one does not exist. Now, let's go to here. What if we let x go to infinity before you take the sine function? Well, if you let x go to infinity before you take the sine function, well, we could just apply that there's a horizontal asymptote. Like 1 over x, the bottom is winning, that's 0. So this thing approaches 0 before it even gets dumped into sine. So if something approaches 0 before it gets dumped into sine, then the limit would be the sine of 0, which is equal to 0. So because like I'm not taking the sine until after I realize these numbers are getting infinitesimally small, tiny, then I know that it'll approach 0. Okay. Now here, kind of in between the two is a ratio. Now don't say it's 1. Right, that's a great trick question. Unless I'm approaching 0, then I know it's 1. We proved that like on, I think, the second day of calculus using the squeeze theorem. But if I'm approaching infinity, I want to know who wins, top or bottom. And the thing is, the top, the top doesn't get any bigger than 1 and any smaller than -1. It's still oscillating back and forth between 1 and -1. But the bottom is getting very large. And so the idea here is that the bottom technically is winning. The bottom is getting larger and larger and larger. Therefore, our fractions are getting smaller and smaller and smaller. They are bouncing back and forth between positives and negatives, but that's okay, because if you think about what that graph might look like, think about a sine wave whose amplitude gets shrunk. And it could still oscillate between positive and negatives, but you're still getting a predictable value of 0 as you go along. The amplitude is shrinking, and so yeah, it does get closer and closer and closer to 0. I can claim that even though this goes from positives to negatives, those decimals are so small, whether they're positive or negative, that we know that the limit value is equal to 0. And why I included these here is I just think that like the AP exam loves to put trig and it loves to put limits on there, and these three functions, or these three limit problems, have very similar, similar structure. They both involve sine functions, but have different reasons or different answers for their limits that we need to be prepared to analyze.